Let's continue. Our next speaker is Yoshihiro Sawano, and he will speak about local Muckenhoupt class for variable exponents. Please.
I'm very glad that I'm here in this form. Actually, so many people suffer from COVID-19 in Japan. We have many COVID victims, and I'm still happy. I'm still okay because I do not have caught COVID-19. But it's very serious for me to live here in Tokyo. So this is why I'm so happy because I can talk. I can present my result in this audience. So today's talk is on local Muckenhoupt class for variable exponents. So what is important in this talk is the local Muckenhoupt class instead of variable exponents. Actually, so local Muckenhoupt class was initiated by Lichkov in 1998 or something like this. So recently, we tried to extend it to variable exponent setting. But what I want to say is that the application about this class. Okay, so let me recall the definition of local Muckenhoupt class. So my goal is to discuss the property of locally regular class AP.local. A locally integral function, locally integral weight is said to be an AP weight if it is positive and finite almost everywhere, and this quantity called AP characteristic is finite. So this is a global condition, but we can define local analogy. So what we want to investigate is the second class. So actually, so when we define maximal operator MF of X, something like this. M corresponds to AP. But if we define local maximal operator, this is additional condition. So M local corresponds to AP local. So how to say? And this is a narrow class, narrower than this class. Actually, so the space class AP local is considered by Lichkov in this paper. And this 2001, I made a mistake. I said 1998, but actually 3 years later. Okay. So importantly, these two classes are related to the local Harris maximal function. Give a meta function f. F denotes the answer maximal function presented just before, and when local stands for the local maximal function. Let me recall the definition once again. So it is well known as the Muckenhoupt theorem that M is bounded on LPW if and only if W is AP, while Lichkov proved that M local is bounded on LP.W if and only if W is in AP local. So my goal, extend this result to variable exponents. Okay. So let me recall the definition of variable exponent Lebesgue spaces. So I have to consider weighted setting. So I add weight in this way. So some people prefer to add weight something like this. But this is what I want to do. This is not what I want to do. So we define the class LP dot. So I suppose that P dot is bounded. Actually, so here, so actually P can be unbounded, but I suppose that P is bounded. In actually, if something happens, is it all right? Can you hear me?
Yes.
Okay, thank you. So forget about this guy and let me define LP.W by using this modular. So when w equals 1, so we have to take it, and then we go back to the classical variable exponent. So what can we know about this weighted Riemann space? Actually, Kreutzlich theorems and Navier prove that M is bounded on LP dot W if and only if W in AP dot. So we'll prove that M local is bounded on LP dot W if and only if W is in AP dot local. So let me give one remark. So suppose M is bounded on LP dot W. Then, so we have a pointwise estimate chi b x r y, excuse me, y times b x r average of f over bxr more than equal to mf of x, mf of y. Excuse me, for y in the body xr. Actually, we need a constant, but anyway, so we have something like this. Then, assuming that M is bounded on LPW, LP.W, we have so this is an easy consequence of this maximal linear quality. So we have a pointwise estimate of MF. So we have something like this. Excuse me. So considering the Springer over this quantity, sorry, we see that this class AP dot is necessary. It seems that some noise occurs. So is it all right? Once again, so let me ask you whether you can hear me well or not. Okay.
Well, yes.
Okay, so you can hear me. Okay, so I have noise here. I don't know why, but anyway, so I think that I can I can speak to you clearly. I think so.
Yeah.
I continue. Okay.
Yes, please go ahead, Yoshihiro. We can hear you.
Thank you so much. Okay, so at this moment, I explained that if the maximal operator is bounded on LP dot W, then W belongs to AP dot. So the same applies to so M local and AP dot local. Okay, so let me give you a picture for this situation. So we have the class AP. So we have AP local, and this is due to Dichkov and ourselves. So we mix on this situation. So we have AP dot. Myself and my student Nogayama. This is Lichkov. And this is Muckenhoupt and William. Oops, sorry. So this is the situation we have. So initially, so Muckenhoupt and we then defined AP, and Lichkov extended to local extension, and Kurzribe and et al. Defined AP dot. So he passed P to the variable setting, and we mix two of them. And this is what I want to say. Okay. So let me give you some examples. So classical situation. So this is the class of how to say Muckenhoupt and Whedon, and this is the class of Lichkov. So the power function belongs to AP if and only if alpha satisfies this condition. But if we consider the local counterpart, so we can remove this upper bound. So this is alpha can be negative, so it can be unsmooth. But if I smooth the singularity at the origin by adding one here, then situation remains the same. But something interesting happens for local class. Actually, for any power alpha, so this is an element in AP local. And this is very interesting because if we set this weight by W, then W of X and W of Y is pointwise equivalent. Excuse me. And this should be something like this. Oops. So we have something interesting. Situation number 4 is interesting. Actually, this will be important in my talk. Another, by the same reason, so we have that exponential weight of order 1. So exponential weight belongs to AP local, but it doesn't belong to AP. So we have a different situation. Okay. So actually, so the bounded AP.W is an AP.local. I want to explain some applications. So two applications will be in order. First application. So I should have said that P is a constant exponent because it doesn't matter if I change P into the variable setting. It doesn't make situation not so difficult, almost the same. So suppose we define the torus T by Tn. So we define periodic LP space by this formula. Here, L over N stands for the set of all measurable functions in Rn. So I suppose that this is periodic in this sense. So if I take K in the periodic lattice in Gn, this translation is the same as F. And we also define that it's known by restricting F into the closed interval 0, 1 to n and take the LP norm. So it is easy to check that LP over Tn is embedded into LP over this class of weight. It is very important that we can take minus n minus 1. Why this is important? So this is because, roughly speaking, in a word, so we have this property. Of course, it is very easy to check, but it's very fundamental. But we cannot guarantee this property for AP class. So if weight is if W is an AP weight, then it is not integrable. So this is a big difference. So for AP class, so we cannot expect that this is integrable. But for AP local class, this is AP local as I explained because it is pointwise equivalent if the 2 points are close to each other. So this is this exponent is integrable. So we have such a good situation. Another technique. Actually, so let me sorry, I should have said that thanks to this integrability properties of L1 property, so we already have this embedding. So suppose we have something here, so we can, then we have a closed subspace. So this is very big, yeah, because we can, so we have a general theory for AP local weights in this space. So this is a closed subspace, so we can readily translate it into this space. In many cases, we have such a situation. So let me give you an example. Maybe I should have set up non-homogeneous. LPW for W in P local. Then we may translate it into periodic, because translate this result into this function space, periodic space. So studying this space is very useful in this sense. So let me give you another example. And so we define LP uniformly local. Is a set of all measure functions f such that this quantity is finite. So f is integrable over any cube of volume 1. Then once again, so we can check that LP uniformly local over n is embedded into the same class as before. So let me give you some situation. So we have defined function f, something like this, but we cut it off at each cube of size 1. So we truncate the cube something like this. Then, so we have a small information here. Maybe I should have said local. So, okay, suppose that I have an operator T satisfying that it is bounded on LPW for each W in AP local. And then T is automatically bounded on LP uniformly local. Actually, so we have an equivalent norm expression. This is important. Uniformly local over n is equivalent with the following expression. So we consider the translate by Zn, that is, and f times this power of weight so and this is so this belongs to AP local. So what we can show about the class in AP local, excuse me, can be readily translated into uniformly local class, and this is very useful. So let me make a final remark about this example. So we can apply my observation to amalgam species as well. Actually, this norm is given by this formula. Okay, so we have some applications about the class of AP local. Okay, so finally, so in this talk, I'd like to explain so why it's difficult to prove equivalence mentioned in the beginning of the talk. So I'd like to show that M is bounded on LP dot W, M local is bounded on LPW if and only if W is a member in AP local. So as I explained, so this is easy, but this is difficult. So I'd like to explain why this is difficult. As I said, so we have 4 different classes: AP, AP local, AP dot, AP dot local. So all of these 3 cases are established. But why do you think this is difficult? So I'd like to explain this. So I'd like to explain the problem. So there are a couple of problems. So first of all, so if I try to mimic the idea of AP dot established by Kurzliebe et al., then we have a polynomial growth of the weights. But this is no longer possible because we have an exponential weight. So this is impossible. So if I try to mimic this situation, this case, so we have a problem because we have a polynomial, we need a polynomial growth. But what happens if I mimic the idea of Lichkov? So Lichkov established the LP local. So we want to apply his idea to obtain LP dot local. So this should be possible. Why didn't you do that? Actually, we have a serious reason. So Lichkov considered AP local with the basis of AP. So he tries to extend his class of AP weight. So let me explain a little more. So suppose I am given AP local, and I'm given a cube here. So we have a weight here. So he tries to consider mirror symmetric expansion. WQ, something like this, something like this. And so we want to try his idea to have a new weight by using mirror symmetric expansion, but this is no longer possible because but exponent can vary, and this is a problem. So we have a problem. So we have to do some trick. Okay, so instead of using the bounded maximal operator in LP.W for this class of weight, so I like to consider dyadic local maximal operator. Dyadic. So this is enough because we can collect many, how to say, 3 to n dyadic lattices, dyadic grids to have a pointwise estimate like this. So we want to control each of them instead of considering this one. This 6 to minus 1 means the R is less than 6 to minus 1, but it's not that important. So I like to concentrate on each one of them. So I fix one of them and consider this operator, only one this operator instead of this operator. So we have a direct variant. So what can I do? In that case, so as I said, it is impossible to use the idea of Lichkov, but we can use another technique. So we have a new idea. So we can manage that. We can extend it in some technique. I skip the detail. After that, so we have to consider m local script d for w in ap.local. But we can also consider it for LP local script D. So we can deduce somehow. In that case, so but here we have much more happier because by our technique we have W in AP dot globals but script D. So generated by this direct grid. So in that after using this reduction, so in that case, so we don't have to use the local variant. Instead, we have considered direct variant. So after this reduction, so we can mimic the idea of Crucible et al. This is my idea, and actually this should work. Okay. So many applications are available. Actually, I explained web characterization, and little page characterization is also available. Okay. This is all that I want to talk. Thank you for attention. I stop here.